This is the screencast for section 6.3, example 9. So in this example, in example 7, we saw only horizontal motion. In example 8, we saw only vertical motion. Now in example 9, there's going to be a vertical and horizontal motion. So both the x and y coordinate are going to change according to t. So first of all, Kevin hits this baseball at 3 feet above the ground with an initial speed of 150 feet per second at an angle of 18 degrees. That's how you know there's going to be both a vertical and a horizontal change. And every problem up until now where we have talked about vertical free fall, it has only had a vertical change. Now this one is going to be throwing a ball with horizontal change. We're not only looking at its height, we're also looking at its distance. So in past sections, when you saw a graph that looked like this, I mean, without knowing it, you were only looking at time and position. You were not looking at how far away the ball was from where it was launched or thrown or whatever. In this example, we're going to look at both the horizontal and vertical positions. Now, the horizontal position, also known as distance, equals rate times time. That's how you're used to seeing a horizontal distance. So in this case, x is going to represent our horizontal position, the rate, well, we'll talk about that in a second, and then times time. So if we look at Kevin's triangle of throwing a ball, I guess, he throws the ball at an angle, and his horizontal rate is part of the cosine of that angle. So the cosine of theta equals the adjacent rate times the, over the hypotenuse rate. So the horizontal velocity over the angled velocity, or in this case our hypotenuse. So our horizontal velocity equals his initial velocity times the cosine of theta. So in our situation, x is going to equal, let's see, the initial velocity was 150 times the cosine of the angle 18 degrees times t. Now his vertical velocity is also part of the triangle. The vertical velocity, which we have studied vertical velocity as not a distance equals rate times time situation. That is what we've been studying in many sections as this formula. But we need to fill in this initial velocity because we don't have a clear vertical velocity, we have an angled velocity. So the vertical velocity is the opposite of theta, the angle he is throwing at. So the sine of theta equals the vertical velocity over the angled velocity. So our vertical velocity, or our velocity along our y-axis, is going to be the initial velocity times the sine of theta. So y equals negative 16 t squared plus 150 sine of 18 degrees t plus the initial position of 3 feet above the ground. Now, in a previous example, we drew a finish line for our two racers, Ben and Jerry. Oh, I just realized that ice cream. Anyway, now we're going to draw this wall, but we don't want the wall to go all the way up into the sky. We only want the wall to have a height of 20 feet. So I'm going to put the ball's motion in x2 and y2, and then in x1, trust me on this, and y1, I'm going to draw the wall. Now, the wall is 400 feet out, so that is a horizontal position. The wall will always be 400 feet away from the y-axis. Now, as far as the wall's height, that's going to be 20 feet. But I want the height to start at 20 feet and go down. So I'm actually going to subtract the same value, 10 times the value of our time. So I'm going to start that wall at 20 feet high, and it's going to draw it all the way down through the ground, but that doesn't matter, and rather quickly. So now as far as our window is concerned, T-min, 0 seconds. T-max, I'm guessing 10 seconds. I have no idea how long it's going to take the ball to go over that wall or hit the wall. I don't know. T-step, we're going to go with 0.01. My X-min, -2. My X-max, I've got to see past that wall, so I'm going to do 450 feet. Ymin -10. Now I'm not really sure how high the ball is going to go, so I tried 50 feet. We'll see. So let's graph that. Now where's the wall? Okay, now wait a second. First of all, this is going way too slow. Second of all, the wall is being constructed as the ball is being thrown. Hold on. Now, let's change my t-step to 0.1. And now let's go to mode and sequential. Let's draw the wall first. Since that is in x1, y1, the wall is going to get drawn first and then the ball is going to get thrown. So now let's see that. There's the wall got drawn. Now the ball is being thrown. Look out, look out. Oh, it hit the wall. So the answer to this question is no. The ball will not clear the wall that is 20 feet away, or excuse me, 20 feet high and 400 feet away. The now try problem number 43 asks us about the same situation, just a couple more detailed questions. So part A, approximately how many seconds after the ball is hit does it hit the wall? So I'm going to hit trace, get to the path of the ball, and it does say approximately, so I do not have to find exact, although I might be able to calculate an intersection. It looks like we are about 400 feet away at 2.8 seconds. Part B, how high up the wall does the ball hit? Well, that's your y coordinate, your position, so that would be 7.34 feet. Part C, explain why Kevin's hit might be caught by an outfielder. So first things first, Kevin's ball could be caught by an outfielder. I mean, they have a tendency to like climb walls, and they're already 6 feet tall, reaching with all their might up to the top and getting the ball with their mitt. I don't know. Then explain why his hit would likely not be caught by an outfielder if the ball had been hit at a 20-degree angle with the horizontal. So I changed the angle that he hit the ball to 20 degrees, just 2 little degrees, and let's see what difference that makes. Much higher. Is it going to clear? Ooh, that is close. I'm not sure if that's going to clear the wall, but let's trace out there and see what happens. That height is somewhere around 20 feet tall as it's approaching the wall, and there's no way somebody's going to climb up or jump up or even reach up to 20 feet high. Maybe a fan, that's about it. So if the ball is hit at an angle of 20 degrees, the ball will be around 20 feet high as it approaches the wall, and no outfielder is that tall or has that good of a vertical jump to reach that high.